As the Minister, Bill Johnston, alluded to before, the importance of PCAM development in the battery industry, my presentation is very much about some of the FBICRC's cathode precursor production pilot plant which we are developing. But first of all, I will cover a little bit more about just the FBICRC before I get into the pilot plant. So the mission of the FBICRC is pretty much to foster collaboration and collective action of our stakeholders in the battery value chain to enable growth in particular areas of the activity in the global battery industry, and to enhance our sort of exports in all the different materials, and also to encourage job growth in education. Currently the FBICRC has about 65 participants involved in there, with 23 of them core key and 42 associates. It's a diverse group of participants with expertise in both the battery industry, ranging in the academic industry and government organisations. Total cash content is about $125 million. The total cash and in-kind contributions, $125 million, was $63 million, and in-kind staff as well as assets like equipment and everything supply the project. Our current participants range from both the mining industry right through to the battery manufacturing side of things, and then the materials as listed in this one here. So the FBICRC projects overall cover the whole battery chain and investment. We're looking at pretty much integrated, as shown here. Just the capabilities in Australia, as I've alluded to by a few people. Most of our work in Australia has been in the mining concentrations with downstream process. I mean, little or no, or only very minor. And from our scene setting project, which was commissioned, which CSIRO ran, the potential for economic growth was identified in a number of different areas, in particular areas like the cathode precursor manufacturing area. And these are the projects currently in the FBICRC, ranging from the waste, cobalt extraction, the extraction side of things, the precursor materials, electrowinning, right through down to the battery layer. So, I guess going back a little bit, I mean, at the stages, currently Australia exports, as we know, most of our main commodities used in the battery industry, but then little of it is actually valued, is incorporated into the manufacturing of it in Australia, as been presented before. And the graph on the right-hand side there, which sort of shows the lithium value chain, will illustrate that very nicely, that even though it's from 2017 to 25, that most of the money that Australia has made has been very much related to the mining and concentrate, but the actual value, even going in the future, is very much downstream processing, in particular, I think the cathode precursor, which, you know, talking about billions and even $1 trillion industry, rather than just the odd $1 billion. So current constraints to Australia to develop a cathode precursor industry has been the sort of lack of the production infrastructure for synthesising some of the quality. NCM, we focused on PCAM and CAM on a pilot scale. Access to the standardised testing protocols are critical for the development of these and optimisation, and cost-effective and environmental and social governance sensitivity process routes include minimising and utilising the waste products in particular. So, in which we'd address some of these pretty much in the running piloting. So the opportunities, obviously battery precursor production is a crucial step to add value to the Australian industry. and there are no facilities available for NCM precursor production here in Australia, although obviously LFP, there's some in other areas, and obviously increased adoption is due to increasing EV. So this is probably reiterating what everyone else has said, that obviously global demand is increasing. This is just showing the lithium-ion batteries in terms of gigawatts, the tonnage of nickel, and as expected, it's going to go through the roof. Australia produced, just to, sort of like to illustrate sort of the costs, it's like production of nickel in Australia in 2019 was about 180 kilotonne an annum, which is an estimate, which at an estimate of say a 2.5 to 3 million tonne PCAM production costs would create a value of in excess of $1.2 to $1.4 billion. Let's need to go back one. The linkage to what we're working in the cathode precursor project fits in with the other programs in the FBIC and integrated into the whole process, from the studies in terms of extraction, for producing the materials that feed into the cathode precursor, right through to electrochemical battery testing and recycling, and even the waste product, other things. So the project aim of the pilot plant is to establish the technical and process capability in Australia to produce a cost-effective and high-quality high-nickel precursor and to minimise the wastes. So the outcomes will have obviously commercial benefits. This is a 3-year project. This was time frame with a total budget of $17 million, of which is 8.8 million in cash and the rest is in kind from our various participants themselves. So the overall participants in this particular project can consist of 4 universities: Curtin University, QUT, UTS, for institutions. We also have CSIRO, BASF, mining companies, BHP, Cobalt Blue, Arena Resources, IGO, Galaxy, and Blackstone, and a few of the materials, Jawproxer and Lycopodium, the engineering firm. So the research team will consist, as I said, of the universities and things. So on the work on the PCAM will be run out of Curtin University, Queensland University of Technology, managing the CAM development of the downstream bit, and simultaneously University of Technology of Sydney will be managing work on high nickel development, looking at the higher nickel cathode precursor materials. Facilities will be developed at CSIRO and will also involve CSIRO in project, and we very heavily involve industry people, in particular BASF, BHP, who's providing some of the facilities, existing facilities in their plant, Jawproxer and Lycopodium, which will do the engineering facilities and studies. So overall, what is the process we're going to use is, there's a number of ways of making PCAM, but the process we're using is known as a co-precipitation method. The reaction itself is straightforward, but it's important to be able to control the reaction conditions to essentially control the stoichiometric distribution, particle size, and morphology. So that's a rough equation there. Metal salts added with ammonia as a chelating agent, and you add sodium hydroxide to precipitate a hydroxide product. You end up with ammonia. But just to illustrate, so this is the 2 stages: PCAM, the precursor cathode active material, and the active material which you feed towards the battery. And there's a number of different variables in the process which control the stoichiometry and which need to be assessed down the stream. I won't go into any more details than that, but things like residence times, temperature, pH control, the type of agitator are very important in the design, which needs to be taken into consideration. So the objects and outcomes the piloting is to, first of all, set up a precursor pilot plant facilities that provide foundation specifications for the development of an industry scale plant. We have then to demonstrate that we can produce at a scale a stable hydroxide co-precipitate NCM precursor. Particularly, we're looking at initially NCM 622 and 811 and a higher nickel value. And then with the suitable morphology, compositional distribution, particle size attributes. And the lithiation to reduce the cathode to meet specifications, electrochemistry. And in addition, also examined, part of the things you end up with a waste product, a sulfate, a sodium waste project, but look at alternative ways of converting that into making, say, a potassium ammonium sulfate fertiliser product, which will add value to the whole process and reduce the costs of the process and be used as a fertiliser. In parallel, there's research that will be looked to conduct, looking at the high nickel, greater than 85% mole percent nickel and low cobalt precursors to enhance the performance of cathode materials tested. At the end of that, of course, establish, and the importance from industry and Australia overall is establish a commercial and technology transfer plan for industry to be able to utilise that results. So in the first stage one has already been complete, which was essentially to develop the framework for setting up the operation. So we stock taking available equipment that we needed, design criteria, the concept, process modelling, purity, looking at the different ways we get resource and materials for operation, the operating costs that we get there. Develop a project planning budget for 3 years. We also did a patent search, which is important for relevant for what we can rather practice, etc. And importantly, is do small laboratory scale. Oh my God, I'm running out of time. Tests. So just from the verification was to look at. This just shows you we have been able to synthesise in a laboratory scale product, which shows nice round particles and homogeneous products from a curtain. QUT conducted tests, and we now got procedures for the doping and coating tests using some of the already synthesised material and develop standardised testing procedures to allow us to, when we get to the piloting. So the piloting part of the work is to developing, to be located at the CSIRO Waterford site in Perth here. Parts of the existing nickel sulfate pilot plant will be retrofit and used. BASF provided us with funding to get fully integrated PCAM units, which have been used by them on our other processes, which will allow fast tracking of progress and allow we've got 4 of those, allow us to change the conditions and flexibility in conditions to ensure that we get a product. Its reproducibility is an importance in the whole process to make a product. Jaw proxer to supply an ammonia stripping and sulfate crystallised circuit, which will be there, and detailed engineering will be carried out by Lycopodium. The CAM met the design, the process, the products from the PCAM products, which meet specifications, morphology and everything through our testing, will then be passed to a QUT, which will then do the series of the lithiation calcination steps, which are in there. And also I mentioned UTS will be doing simultaneously synthesising higher nickel and looking at some of the other products to keep ahead of the case. So overall program is pretty much, so we split up into sort of 3 universities, although it's all work together. We've got a project management committee team with some industry representatives. It's important to keep the stakeholders all involved in the whole process, and committee meetings. We've done a few, have done a hazard already on some of the work and everything else, and risk assessment to ensure that everything will run smoothly. So the next step is the design and development, which we'll be doing more test work, designing the piloting in both places, Modifications will take place later in this year, and then we will systematically do test work at the end of the year, starting at the end of the year, to make 622 and at a higher reproduction scale. So the whole overall program, we've completed the first stage, engineering, lipopotent doing the engineering. So the next stage is in the second quarter, third quarter, with the plants, the pecan plants will arrive from Germany and Jaw-Proxer, and we'll put it all together there and start our campaign for 18 months conducted. At the end of there, establish commercial transfer plan, and once the program is finished, we will then set up, the facilities will be set up at Curtin for ongoing validation test work to our industry. So just quickly, as the benefits to support and accelerate, the benefits is to support and accelerate the industry to develop the cathode, which is in Australia, to demonstrate the production, establishment of facilities, to allow mining companies to perform testing and validate performance, primary commercialisation pathways, which is important in development, potential to generate commercial technology, cost-effective ways of